In 2b, we will try to model the log returns using a GARCH 2.2 process. In a GARCH 2.2 process, we assume the log returns are given as some volatility multiplied by noise random variable Zn, which, well, I guess in the lecture notes we call them IID. We assume they are ID normal random variables. In part A of exercise 2, we assume that the Z are symmetric random normal variables, which are continuous in distribution. I guess both assumptions work out pretty well. So let's just say we assume Zn are IID symmetric and continuous. And apart from that, we shall also remember the important assumption that the Zn are independent of the volatility sigma n. Also, particular for the GARCH 2.2 process, we have that the volatility satisfies a recursion that describes for us how the volatility in the period n depends linearly on the square of log returns in the previous two periods and also the square of the volatility in the previous two periods. So we have this here, and what does the exercise ask of us? Well, in the exercise, we are asked to let the symbol Vn denote a vector given by sigma squared, the volatility in period n+1 squared, and then the volatility in period n squared and Rn squared down here. Okay, and also we are, after we define this notation, we are asked to show that Vn satisfies a certain recursion, and the recursion it satisfies is of a linear nature. So we're asked to show that Vn satisfies this recursion here. In the exercise, it is specified that An is a 3 times 3 matrix and Bn is a vector. And common sense dictates that Bn should also have 3 rows. And after we figure out which recursion Vn satisfies, we are asked to assume that the limit of Vn for n tending to infinity exists. And denote it by V. Find the stochastic fixed point equation satisfied by V. So the rule of thumb whenever you have an exercise with stochastic fixed point equations is this. If the limit of V for n tending to infinity is assumed to exist, and we already have a recursive equation for Vn, well then the stochastic fixed point equation is simply found typically by replacing some stuff with an identical copy which satisfies some things distribution-wise. I'll get back to how we do this later. And then 2, let n tend to infinity on both sides of the equality in distribution sign. So this is the case where it's easy to find a stochastic fixed point equation. It's easy if you have, if in the exercise it is given that the limit exists, and if in the exercise you have a recursive equation available. If you do not have the recursive equation available, first you have to write up the recursive equation. Sometimes that's easy, sometimes it can be quite hard. And also, if you do not have the assumption that the limit exists available, then either you have to write down that you assume it on your own, or you will have to prove that the limit exists, which is one of the things that Jeffrey does in the lecture, in the PDF note that he has uploaded on stochastic fixed point equations in relation to GARCH processes. There he does a lot of shift operating and different kinds of recursion gymnastics, and one of the reasons that he does that instead of just replacing something with an identical copy, as we will do here in a moment, is because he needs to show the existence of the limit first. So since we're allowed to assume that the limit exists here, we are actually, well, there's a lot of work that's been taking off our hands here. Anyways, enough talking. Let us start by solving the first part of the exercise I, where we want to find a recursive equation that this vector satisfies. See ya in the next exercise, in the next video, where we do exactly that.